Okay, let's continue on Lecture 7 with pre-allocation. This is not necessarily something really in the book, but it is something I think that is very important because it was something that was done, at least when I was introduced to it around the Apache web server in the mid-90s. And it was an idea that I love in the whole computer science mindset of, the idea that we understand that fork and exec are expensive calls. They're needed for certain things, but they're not the best way to deal with concurrency for things like, answering, an index.html 200 bytes of data. So how do we do something that might work better? And the idea of pre-allocation is, I said, well, why don't we just have a whole bunch of them sitting around waiting? And the interesting thing about that is I think that a lot of people look at this and they think that what happens is the parent of all the children gets all the requests and then it gives the children work to do, which is not the case. What it is the parent is there just to manage that the child processes are running, but the children process all together say that they want to sit on accept and they want to listen on the file descriptor that is the MSOC from what we've seen in our code. And in doing that, there's no reason for them all not to be able to do that and call accept, because they're all independent processes, and there's no issue with each one of them sitting in a blocking call. But that's the beauty and the elegance of HTTP more than anything else, is that we don't care who answers that question. So do we need to know that last time the fifth child process dealt with it, we need to go back? No, we don't care. And in reality, it's best that we don't. And the only thing that the parent process really does is it knows if some administrator like me, when I first started, wanted to go in and start killing all the processes to try to restart it. I got very frustrated because every time I'd kill one, a new one would pop up, and then I'd get fancy and write a little shell script, and I'd kill 7 of them in a row, and 7 more would show up. So that was really the goal of that parent process, was to know that that SIG child came in and to spawn a new one. So the idea really is around a parent managing child processes that all sit at the accept call at the same time. Now, this will not work for an SSH server. This will not work for many other protocols. It only works for things that are, TCP. It would work for UDP. I guess there's kind of, an interesting way to think about, how that would work. But let's say TCP, it is a form of concurrency, but it is something that is stateless, meaning it doesn't matter which one it goes back to. If it has to go back to the one it just talked to, it ain't going to work. So it works very good for HTTP. I think I did put this in here. Let's see if... Here's a version of pre-allocation. I kind of took the code that was there and kind of rewrote it, I think, if I remember right. Yeah. So here what I did is I just created 10 child processes. And what I did is I just fired up each one. And if you were a child, because every time you'd fork, and every time it would fork, there'd be a parent and a child that would come out of it. I would call exit on this TCP echo D, and then I would sit here in this while loop and take a request. Nothing fancy here. This is echo, the HTTPD. And I don't expect you to do this for Lab 1, but I just wanted to give you kind of the flavor of, creating a pre-allocated server is not a tremendous amount different than what we did with threading in terms of what it would take to code it. But the idea behind it is kind of radically different. Let's go talk a little bit more about asynchronous I/O. We talked about this in class last time, but I think it's an interesting one to think about where this really works. And I say that it works well with low I/O, meaning small amounts of data over long periods of time. And where this would work best is something where random things might come in every 10, 20, 50 seconds. Little amounts of data, don't require a lot of back and forth, because if you think about how the mechanics of how this code works, if 1,000 things all came in at the same time, excuse me, the code would actually run iteratively, meaning it would deal with connection 1, then 2, then 3, then 4, then blah, blah, blah to 1,000. There's no value in that. If instead I take the other bad way, so the one bad way would be a lot of frequent connections. The other bad way would be a lot of data that goes back and forth, because the same thing would happen. Even if I only had 2 or 3 of them, each piece of code would, let's say we're transferring a gig and it's doing 100K at a time, then what it's going to do is it's going to do the 100K, then go deal with the other guy, then go deal with the other guy, then come back and deal with 100. So not really super valuable. So different ways to kind of think about it. Again, there's 2 ways to do it. We're only going to see the select version. Poll is kind of the same exact thing. It kind of works in the exact same way. Same mechanism. The only real difference is poll deals with a vector instead of a bit string or bit bucket or bits in a row. And the only real big difference is poll gets down to, I think, millisecond level, and select is only second level for timeout. So not that big of a difference. It works by setting up, again, this grouping of descriptors you're interested in. And the biggest thing you got to keep in mind, this does not work on regular files. This doesn't work on, /user/include/standard.ir.h. That's a regular file. The problem with a file like that, or standard in, standard out, standard error, as comes, with every given process as well, is they're always there to be read or written or whatever. So there's no mechanism to sit and block. It only works with 2 special kinds of files, which are sockets and pipes. We're only dealing with sockets in this code, but pipes are somewhat analogous in ways to pass data between different processes. They just don't go outside of the OS. So the idea is we have to sit on these things that, I've heard people term them as slow system calls, meaning, well, I could sit there for a millisecond or I could sit there for an eternity if nobody's sending me data. So what does it really mean and how does it really work? So we can only do it on things that are defined as sockets or pipes. We'll just say sockets from now on. And as we sit on that socket, we want to know 3 things. Can I read? Can I write? And is there an exception? Almost all the time, we really only care about can we read, because if we write and it doesn't work or whatever, we don't really care because that could block us forever as well. And we don't want to, lose out in memory leak and all the other bad stuff that comes with that. So normally we just want to know, is a new client coming in and did they give me some data? And that's really kind of the big algorithm around all this. The master socket is going to be one we deal with a little differently, because when the master socket has data, that means a new connection's coming in. We need to manage it. We need to call accept. We need to go deal with it, move on. And then all the rest just mean that they've already been connected and we're just doing I/O until they're done. Now, again, let's put this in the frame of reference. Will this work really well for an SSH server? No, not at all. The reason why is the SSH server, even though it's infrequent data and it's little data, it's a connection that's bound up for a very long time. So what will happen is this thing will try to go manage this thing for a very long time. Well, and there's a major problem in the fact that SSH needs to call fork and exec a new shell and overlay everything you did. So then you just blew away all this code. So that doesn't work. HTTP could work. It's just very inefficient. And the fact that we know that when you go ask for an index.html and it's got 10 graphic files, those are 10 separate connections. There's 11 solid connections. You don't want this thing to manage all that because there's just no point. So it's not a good one for that. It is good for daytime and what we'll call the super server. We'll talk about that in a second. But, as I talked about last week and as we walked through it, there's only one real way to do this. So the whole algorithm, everything is, kind of cut-paste in a way because there's no real other way to do it that well. The idea is that we're going to iteratively sit on the select call, select the value, and what select will do is select actually tells the kernel, hey, let me know if any of these things happen. And then when it happens, that means that the select call returns. So the select call is actually just sitting there waiting and listening on the kernel to do something. When that thing happens, whatever it is that I've turned on, and that's why in select we use those bits, whichever, let's say, light switch we flip from 0 to 1 comes back, which could be 1 or more, or it could be the timeout, then we have to go figure out, well, what happened, because the kernel doesn't come back and say, oh, hey, it was 1, 4, 6, and 2. No, it comes back and says something happened, and we have to, as coders, have to go ask what happened. And it could be that something came back from accept, or something came back from the master socket, any of the slave sockets, or it could have been a timeout. So again, here's the function call. And the interesting one, and I talked about it a little bit, this N is very, very, very important, because it's one of the most frustrating things, I think, in some forms of computer science. And I always joke about this when I go to a hotel and the ground level is 0. I know it's a German hotel because they had it right. 0 is where you start. Most people start at 1, and that's how we think about things. So if we think about, let's say we open up a brand new file and it's file descriptor 4. If we pass 4 in here, then what 4 is going to do is it's going to watch for 0, 1, and 2. So, or I'm sorry, 0, 1, and 2, and 3, because that's 4 of them. But it's not going to get the 4th one. So I always kind of name this one N plus 1. So it's whatever your max file descriptor is plus 1. And I've actually just, every time I've done this, I've just put in that code to say max FD plus 1. So it's a little weird one, just from the fact we're starting at 0. We have our 3 sets, our read set, our write set, and our exception set. And these are those bits, and they're just simply, think of a string of bits. If 0, 1, 2, we know our standard in, standard out, standard, turn them to 0. But maybe we care about the MSOC is 3, turn that to 1. 4 is a new slave sock, turn that to 1. So we manage these sets all the time, and you'll see that in the code. Normally, we only deal with the read set, write set if you have a good reason and definition to do it, and exception is just one that if you can actually manage the exception and do something with it, put it there. And then we have our timeout. The timeout can be 0, which means don't have a timeout, or it might be something you want to come back from. So here's that max FD plus 1. I would just write that in the code, because I've got burned so many times on putting in, whatever that max FD is, and oops, that's not the one I want. There's some other helper functions that come with it. FD0 is a clean, or a nice one that's like memset and B0 and all the rest. Clean that set up, turn them all to 0s, because when you get a set of data, it's all 0s and 1s by random set. So FD set turns one on, clear turns one off. So clean it, set it, unset it. And then this is the question. Is the reason that select return because of you? Is it because of file descriptor 3 in read set? Is it because of file descriptor 10 in write set? This is the questions we have to ask. And keep in mind, it can be more than one, so you'll see that again in the code. So this is the code. It's also the example in that pilot code that came in that example directory in the V3 Linux out of the book. But the idea really is, and I just cut out the meaningful pieces here, is we're going to go set up all these sets. We're going to say we care about the number of file descriptors, and this is plus 1. We care about the read set. We don't care about the write set. We don't care about the exception set, and we don't have a timeout. So all we care about is this read set. The select call will sit there in a blocking state, and it will say, I will sit here until something happens. Now, I didn't show you what was set up beforehand, but let's just say that the only thing that was set up is the master socket. The first time we come through, we're going to say, oh, was it the master socket in the read set that was the reason why this thing returned? If it was, then we do this work. If it wasn't, then we drop down here. But even if it was this, we're still going to drop down here, because what we need to do is manage file descriptor. Let's say it's 3, and then 4, 5, 6, 7, 8, 9 to whatever's available or open. So when select returns, this is the whole algorithm right here. What we're going to do is we're going to say, is this a new connection? If it is, we're going to create a new SSOC that is in this block scope, so it only exists here. Notice this is another block scope. If it is, then we're going to set it. We did nothing more than go up to this set that's right here and flip that switch on. And then what we're going to do is we're going to fall through this, and then we're going to go back up here, because just because I've set it doesn't mean that it's something I care about here. So let's say that the first time it comes through, new client comes in, it goes back up here. The client obviously has something it's not going to be this. It's going to go through these file descriptors, which we shouldn't start at 0, just to clean the code up a little bit. We're going to basically walk through all the file descriptors, and we're going to ask that question. As long as it's not the master socket, and I would argue 0, 1, and 2, then we're going to ask that question, was it you? Was it you that returned? If it is, then what I'm going to do is I'm going to call echo on that, and I'm going to close it, I'm going to clear it, and I'll move up. This is a very dumb example to really have here because we're only dealing with this thing once. A better example would be as if there was iterative, some amounts of data kind of going through here where maybe file descriptor 4 and 12 came back, and then 6 came back, and then 9, 10 came back, and, we're kind of spinning. This is kind of ridiculous. I would argue this is a better iterative because if you're just doing this one thing, do it, move on. So, my opinion. Now, where this really got us to is this idea of a super server, and the super server kind of took off from this idea to say, okay, well, maybe we don't have a lot of connectivity, but we don't really want to write a bunch of socket code. We don't really like socket code. So there was this idea of this thing called inetd, and then there was xinetd, and then there's all these new ones that have come from it. But the idea was, why don't we create this thing that'll sit there and listen for all these things, and when they happen, we'll just kick off the appropriate program and let it run. And this is actually how most of the base connections worked back in the day. So when we looked at echo, daytime, time, even telnet and even FTP, and some of these early things were actually born out of one server. They would listen for everything, and when that one thing came in, it would fork and exec that new process off, let it run for whatever time it was, and then go back. So really what a super server does is it listens for many protocols at the same time, meaning it can listen for telnet on 23 TCP, it can listen on FTP on 21 TCP, it can listen on 53 TCP for DNS, it can listen on all kinds of different ports, because we've used select now to say, tell me when any of these come in. I couldn't do this if I don't have select, because I can't sit there and call accept on more than one tuple at a time outside of using select. So I think if we've got an example here. So this is the super server. And so what they did is they got fancy and created this service thing. This actually used to be a file called etc/init tab. And this was the thing where it would set up kind of the same thing. And there's a few of them here. So it would say, I want to listen for echo. It's a TCP service. I'm going to use no socket. And this is the function that they use. In reality, what we used to do is we would call exec and spawn a new function, like you guys are doing with CGI. So this is a way to kind of set it up. And then basically we just get into that same loop. And a little fancier here, but we clean this thing up and we just kind of set all these different pieces up. But then here's our whole thing here with our loop that goes forever and our sets. The only difference we do is we just ask if it's set. Instead of just calling a function, we call the function that it's meant to call. So here's my DCP and what I'm going to do with it, my function, versus which they're passing in here, versus the actual way that this was done back in the past is that you would actually call fork to create a new process, then call exec on that one and let that do the IO, exactly what you're doing with kind of CGI today. So that being the end of lecture 7, the main thing to think about here is for lab 1, how do you add that pthread create to your code? You don't have to worry about locks because we don't have race conditions or we don't have critical sections. And really all you're doing is you're just creating that, the threads. The one thing that the assignment does do is it says print out the thread, so just for you and me to see, it's creating more than one. At different times. I don't think you're ever going to be able to exercise it enough to show that more than one's running at the same time, which is kind of difficult in reality. I'm sure you could write some fancy code with, some other ways to not through a browser to go get at stuff, but that's really kind of the piece for that. So with that, please drop me an email, give me a call if you have any questions on any of this. Otherwise, we'll see you next week.